Hello guys, welcome back to our lectures. We're gonna continue talking about arithmetic operations in MIPS microprocessors in chapter 3, and this time we're gonna talk about multiplication. So multiplication is a very important operation that most processors do. Although it's less frequent to appear in instructions, maybe 100 times less probability to appear rather than addition and subtraction. So for multiplication, let's start first by to see how we can do on a paper and a pen how to do multiplication. Okay, so first we have two numbers to multiply together. So we call the first one multiplicand, the second one multiplier. Okay, can we switch? Yes, you can switch. Of course, the internal results here will be changed, but the final answer of course will be the same. Okay, so it doesn't matter. So let's see how multiplication is performed in binary. Basically it's exactly similar to decimal multiplication, except that we have just zeros and ones, so it's exactly the same. Okay, same operations. So for example, let's start by the first. So we take one, the first digit of the multiplier, basically here's the first bit, and multiply 1 by, let's say, 1000, or of course it's 1000 in decimal, but it's not 1000 here. It's basically 1000, which is 8. So when we multiply 1 by 8, it will give us just 8. Then we should go to the second bit, but before that we should shift left the second operation by 1 bit. So we're gonna put 0 here and multiply 0 by 8, 1000. Of course this will give us just zeros, those 400. Then we go to the third bit, but now we shift 2 bits, so to 00, and again 0 multiplied by 8, which is 1000, will give us again 4 zeros. Finally we have 1 again, but now before that we have 3 digits or 3 bits shift, and 1 multiplied by 001, which is 8, will give us 8. So it's really easy, really simple, but it's a long operation because you have to repeat it with the same number of multiplier bits. So if the multiplier is 4 bits, you have 4 internal multiplications. If it's 5 bits, you have 5 internal multiplications. Okay, then you add these 4 numbers together. 0 plus 0 plus 0 plus 0 will give us 0. 0 plus 0 plus 0 plus 0 will give us 0. 0 plus 0 plus 0 plus 0 again 0. Then 1 plus 3 zeros, you give us 1. Here you can consider this 0. 0 plus 0 plus 0 plus 0 plus 0 again 0. Then you can here put 2 zeros and again 5 zeros here. Then you can put 3 zeros and this will give us 1. Okay, so the final result is this result here. This is basically just to confirm, this is 8 and this is 9, so this should be 9 by 8. This should be 72. Okay, 72. Let's check. This is basically 8, 2 to the power of 4, 2 to the power of 5, 2 to the power of 6, which is 64. So 64 plus 8, this is basically 12 and 7, so 72, as we said. Okay, so can we change the multiplier and the multiplicand again? Can we make the multiplication like this? Yes, of course you can do it. Okay, and it should give you the same result, 72 again. Okay, so when we might have a difference. We might have a difference if we have less number of bits in one of the operands. Like for example, multiplying, let's say 1000 by 11. Okay, so in that case, which is basically 8 multiplied by 3, which is 24. In that case, we're gonna have like this. Then again we put 0, and we're gonna have like this 0 0 0 1 1. Okay, this is 24. 2 to the power of 8 plus 2 to the power of 3 plus 2 to the power of 4. So 16 plus 8 is 24. Okay, so you have here two internal operations only. But if you multiply, let's say 1 1 by 1 0 0 0, then you're gonna have 4 operations here. Okay, 4 operations. For example, 0 multiplied by 1 1, it will give you 0 0. Then we're gonna shift again 0 0, shift again 0 0. Then you're gonna have at the end 1 1. So we're gonna have 1 shift, 2 shift, 3 shifts. Okay, so it's same result, but you have 4 operations here in the middle. So the delay will be doubled because you have here 2 operations, you have here 4 operations. That's why we needed to make distinction between the multiplicand and the multiplier. Okay. Also in MIPS, we always assume that we have 32 bits because the registers is only 32 bits. So we don't have this problem. Okay. So let's now explore how we can do this in hardware. This is the first circuit. I call it circuit 1. Okay. That can do the multiplication basically. So we store the multiplicand in a register, but this register is 64 bits. Remember, in MIPS you have 32 bits. So what's gonna happen is basically you're gonna store the multiplier real value in the the least significant 32 bits. And just put zeros here in the most significant 32 bits. Okay? And as we see here, let's go back. As we see here, each time we shift. Basically shift left. So basically here with each operation, we do shift left. So we have here a control circuit. This control circuit will do basically, first, it will decide either we have, addition or not, and also it will decide for the shift. Okay, so and we're gonna decide whether to have a shift or addition or not based on the multiplier. So we have another register. So this is register 1, 64 bits. And this is register 2, but this now only 32 bits. It's okay. And we have another register 3, which is 64 bits, because one note here that we didn't mention is that the output. So if you have a multiplier of n bits, and multiplicand of m bits, so the output will be n plus m. So in our case in MIPS, we have 32 bits all the time. So the output will be 32 plus 32. It will be 64 bits. Okay? And here is, the algorithm under which this circuit will work. So first we're gonna start by, of course, product equal to 0 initially. And then we start by checking the multiplier least significant bit. Okay? If the least significant bit is 1, let's start by is 1. So we're gonna add the multiplicand to the product, which is the result. Okay? And place the result in the product register. So we're gonna overwrite it. Okay? And if the multiplier least significant bit is 0, we will not do this. So we're gonna go directly to the second, operation here, which is shifting the multiplicand register by 1 bit to the left. Then we shift the multiplier register by 1 bit, but to the right. So here the multiplicand to the left, the multiplier to the right. If we go back here to the example, why is the multiplier to the right? Because we start first by this bit here, then we go to the second bit, then the third bit, then finally the most significant bit. Okay, so when we shift, so in the beginning it will be like this. When we shift one bit, it will be like this. And the bit, so in the first operation we cared about is the least significant bit. So we need this bit to be the least significant bit. That's why we made the shift right. Then in the third operation we care about this bit here. So we're gonna shift right again. So it will be 0, then 0, 1, 0. Then in the third operation we're gonna shift right again. So the one bit, the last bit, will be again under control here, or in the picture. That's why we make the shift right in the multiplier, and we make the shift left in the multiplicand, because each time we shift the multiplicand to the left here in each step of the multiplication with each bit in the multiplier. Okay, good. And for the addition, not to repeat the addition operation, so we start by adding these two together, then the result will be added to this one, then the result will be added to this one. Okay, but we will not do the addition if the result is 0, so this addition will not be happen, and again this addition will not happen, because, and we only add this one to the first to the last, because these are the non-zero the non-zero values, because the least significant bit and the most significant bit was non-zero values with ones. Okay, that's why here if the least significant bit of the multiplier is 0, we don't make the addition, because it's basically we're gonna add to 0, and if you do the addition still you're gonna get the a correct result, but there is no value of doing this. You're gonna consume power for nothing, because the addition result will be the same, will not change. The value in the product here will not change. Okay, and how many times we're gonna repeat this? We're gonna repeat this according according to the number of bits in the multiplier. And the multiplier all the time in MIPS is 32 bits, so we're gonna repeat this 32 times. So once we reach 32 repetitions, we are done, and the result that we get is basically the result that we want. Good. Let's see an example in action, step by step, how this circuit will work. So let's assume, of course, not 32 bits, because it will be very long. But let's do a 4-bit, numbers, simple ones like 2 multiplied by 3, which is basically 6. Okay, we're gonna assume the 2 is the multiplicand and the 3 is the multiplier. So we're gonna do step by step. Okay, so let's have like iteration. Step here means what's gonna happen basically in the step, and multiplier, multiplicand, product. So first, in iteration 0, of course there's no iteration 0, this is basically the initial value, the initial state. So we're gonna consider the 3 as the multiplier. This is basically 3 here, and the 2 is the multiplicand. And remember, the multiplicand register is 64 bits in MIPS, because basically the multiplicand is 32 bits, so we're gonna append it with 32 bits zeros. Here we have 4 bits, so we're gonna have the multiplicand register 8 bits. We're gonna put the multiplicand here, and this will be just zeros. That's what's gonna happen here. This is the 2, and this is the zeros that we mentioned. And the product initially is just zeros. So in step 1, each step we do multiple steps actually. So in step 1 we're gonna have multiple steps. First we do the addition. If we go back, I'm gonna go back here, just to show you guys. So between that point and that point, okay, we do 3 steps. This one, this one, this one. Okay, we might skip the addition, but we have to shift right and left in the multiplicand and the multiplier. Okay, so in step 1 we should expect 3 states or 3 steps, 3 internal steps. First, we check the least significant bit of the multiplier. It's 1. Since it's 1, we're gonna add. We're gonna add what? We're gonna add the multiplicand to the product. So we're gonna add these two values together. And of course, this is just zeros. So we're gonna have here 4 zeros and 0, 0, 1, 0. Okay? And this will be the same. This will be the same. Then we shift left the multiplicand. So we're gonna shift left the multiplicand. So we're gonna add here 0 at the least significant bit, and of course this bit here, the most significant bit, will just disappear. Then the third internal state, it's shift right the multiplier. So we're gonna shift right in that direction. So we're gonna put 0, and this one will be the least significant bit. This is step 1. Step 1 has finished now. Now we're gonna go to step 2, but we check first in step 2 the least significant bit of the multiplier. It's 1. Since it's 1, then the first internal step in step 2 is basically the addition. So we're gonna add this one, the multiplicand, to the product. 8 bits plus 8 bits. So basically this will give us, 0, 0, 0, 0, 0, 1, 1, 0. And multiplicand is the same. Multiplier is now the same. The second internal step is shift left is the multiplicand. So we're gonna shift left and add 0 here. The third internal step is to shift right the multiplier, so it will be all zeros. Okay. As we see here, as we go internally here, the multiplier and the multiplicand just change it. Okay, but this will not affect the final result, as we're gonna see now. Now before we go to the third step, we check the least significant bit of the multiplier. It's 0, so there is no addition. No addition. Look, it's the same. Then shift left, shift right the multiplier. Before the fourth step, because we have 4 bits, so the number of steps should be 4. It's 0, again no addition. Shift left, shift right. Okay, and here is the result. And really 2 multiplied by 3 is equal to 6, and this is 6. Good. Now the question is, can we do better? Yes. This circuit does better than the previous circuit. So what we have done here is basically, first in hardware and also the delay. So the multiplicand here, as we see, is only 32 bits, not 6. So here we save 32 bits, or we need less, smaller register, we can say, for the multiplicand. And if we go back and if we draw the original circuit, we have here the multiplier register 32 bits. Here there is no multiplier register. Okay, but what we have done in here is that we replaced the least significant, or we initialize the least significant 32 bits of the product by the multiplier. Okay, and we do the shift now, not to the multiplier, but we do the shift to the product itself. So we have 2 internal steps in each big steps. The first step is that the addition, and the second step that happens, is basically, the shift right of the product, as we're gonna see. So we have 2 internal steps, so we are expecting now faster circuit, although it's not much faster than the other one, but it's still faster. And we save also the hardware. So here is a summary of so basically have the size, and we get rid of the multiplier register. Okay, so let's check the algorithm under which this circuit will go, or will. So basically from this point to that point we have 2 states, or 2 internal steps, not 3. So that's why it's faster. Now we will not check the least significant bit of the multiplier, but we're gonna check the least significant bit of the product. Remember, the product, that's the product register, is initialized by the multiplier here. One may say, but we mess up now with the result. No, because the shift, because you're gonna shift each time, shift right the product, so this will disappear, and gradually, step by step, you know, the result of the multiplication will overwrite this one. So we are okay. So if the least significant bit of the product is 1, we're gonna do the addition. So we're gonna add the multiplicand to the left half only, this half. So this is the left half. This will be added to the multiplicand. Of course, only if the least significant bit is 1. Then we shift the product register by 1 bit. Shift right here. This should be mentioned. Shift right. Okay. And once we did this 32 times, then we are done, and the result that we get in the product register is basically the final result. So let's see 2 examples, not just 1 example. Let's first redo the 2 by 3 multiplication. Okay, again the 3 is our multiplier, and the 2 is considered here the multiplicand. And we're gonna repeat this for 4 times, but each iteration has only 2 internal steps. So now we don't need multiplier location, we just need the product multiplicand. So the initial value, look, here's the product, it's not zeros, it's 0, the most significant 4 bits is zeros, but the least significant 4 bits is the multiplicand, the 3. And the multiplier, not the multiplicand. And the multiplicand is just the 2. So the first step, or the first iteration, has 2 internal steps. First, we check the least significant bit, which is 1 here. So we're gonna do the addition. We're gonna add the product to the multiplicand, but the most significant 32 bits. So we're gonna add this value to these 4 zeros, and of course this will give us 0 0 1 0. The second internal step in step 1 or iteration 1, we shift the right the product. So we shift right, so we're gonna add 0 here, and we shift right, so of course this one will disappear. Second step, we check the least significant bit, it's 1, so we're gonna do the addition. Again, we add this to that, so it will give us 1 1 0 0. Then we do the shift right to the multiplicand, so we're gonna shift right and add 0, so of course this one will disappear. Now we have 0 in the least significant bit, so there is no addition, so this will be the same, no change. Then we shift right again, we add 0. The fourth step, the last one, again we have 0, so there is no addition, same here. And we shift right, again we have 6. Okay, good. Another example. Now we're gonna do this on the circuit itself, so we can see how the circuit will behave. Now we're gonna multiply 6 by 5, so we're gonna consider the 6 as our multiplicand and the 5 as our multiplier. Can we switch them? Yes, we can switch. Although the internal operation will change, or the internal results will change, but the final one will be, which is 30, will be the same. So the initial state here is that the multiplicand register has 0 1 1 0, and the product has 4 zeros in the most significant 4 bits, and the least significant 4 bits will be just as a multiplier, 0 1 0 1, which is 5. So the first step, the first iteration, we have here 1 in the least significant bit of the product. So we're gonna do the addition. Look here at 1. 1 means make addition. So this control circuit will control the ALU. This ALU, this is basically an adder here. An adder circuits that do the addition. Of course, this is not our topic now, but you should know there is a digital circuit that can do the addition for you. And we control the circuit with the control module here, which is another piece of hardware that we don't care about right now, or we are not considering right now. Then we do the shift left. We should do now the shift right of the product. So the product, change it to this value. Then we shift right, and this will change it to this value. Then we check again the least significant bit, which is now 0. So there is no addition. Look, it's now 0. So this circuit will not work. And we do shift right again. Now we have 1. So we're gonna do the addition. 1 here. And then the shift right. Now the final iteration, we have still 0. No addition. And shift right. And this is basically the final result, which is 30. Okay? Can we do better? Yes. So now with according to Moore's law, if you guys remember from the 8 great ideas, we double the number of transistors almost every 2 years. This is years, for example. Okay, so we have a linear relation. Each 2 years we double the number of transistors. Okay, so what's gonna happen now is that we can integrate more multipliers, basically more of this circuit. Okay, on the chip, on the processor. In our case, MIPS processor. So what we're gonna do is basically, since if we go back here, we check each bit here in the multiplier, and we do another iteration, right? So what if we basically have 4 circuits of that one, and for each one we just have we just need to know the corresponding bit in the multiplier. So the first circuit will have as input 1, the second circuit will have as input 0, the third will have 1, the fourth will have 0, which is basically the multiplier 0 1 0 1. Okay, and each circuit, so you have a circuit, another circuit, third circuit, fourth circuit. This takes, all of them takes the multiplier, the multiplicand, which is 6, but the multiplier bits will be just divided right now. So this will take 0, this will take 1, this will take 1, this will take 0. So what's gonna happen? This gives you the one internal result. So internal result 1, internal result 2, 3, 4. Okay, then you add these together 2 by 2, then you add these together to get the final result. What gain? So we doubled, of course. Here we have, we replicate the hardware, which is of course more cost, but now we reduce the delay because we don't have to make the iterations. We also can make some sort of pipelining, and we're gonna explore the pipelining a lot in this course, but not now. In the future, chapters. And so we can now make the circuit faster in 2 ways. First, by parallelizing the operations, and also using pipelining. Don't care about for now about the details of this pipelining stuff, but it will be much more clear in the future videos for future chapters. So here is the architecture for 64 when you have 32 bits basically. So again here, as you see guys here, so here is one result which is basically come from bit 0 of the multiplier, and this is the second result that came from bit 1 of the multiplier, bit 2, bit 3 until bit 31, of course 32 bits. So you're gonna have one circuit, two circuits, until they should be like 31 circuits. Yeah, 31, not 32. Just try it, it will be 31 circuits. Okay, so this is basically will be, as we said, fast, but of course you're gonna consume some resources. But with the evolution of of Moore's law, the cost is not that high. Now let's see the instructions that MIPS use to do the multiplication. Okay, so we said that any multiplication will result in 64 bits, because in MIPS when you multiply two registers together, each register 32, so the output should be less than or equal to 64 bits. Okay, but there is no register that have 64 bits, because all registers in MIPS is 32 bits, because this will make the design faster and simpler. So for this reason you have two registers in MIPS, one is called high, one is called low. So the high register will store the most significant 32 bits, and the low LO will store the least significant 32 bits. Now what is this instruction? The instruction is called mult. So when you said mult RS RT, this basically, and also mult unsigned RS under, so this will be basically multiply RS and RT, and the result will be in high low concatenated together. Okay, now if you wanna use for example the result in high or the result in low, okay, you cannot use them directly. You cannot use the high and low registers directly. So what we do is basically we should transfer them first to other registers. So to transfer them, we have two instructions. One is called move from high register to some destination register, whatever. Move from low register to some destination register. Like for example, move from high, register T0. So T0 will be basically equal to high. Okay. If you are sure that the output will be less than or equal to 32 bits, then there is another instruction called mul. Like for example, 2 multiplied by 3. So 2 is 32 bits, can be expressed in 32 bits. 3 is also can be expressed in 32 bits. And the result 6 is also 32 bits, or can be expressed in 32 bits. Of course, they are only 4 bits, but I mean, still, if for example you have a register which is T0 equal to 2, and a register called T1 equal to 3, and you want to save the register in, for example, S0, so S0 will be 6, and there is no overflow or stuff like this. Okay. So here, RD will be the destination, and the multiplicand and the multiplier is basically RT and RS. That's it, guys, for this lecture. Thank you very much for watching, and see you in the next lecture. Bye bye.